Water is such a unique compound that it gets a section in this chapter all to itself. Water has a very low molar mass, 18.02 grams per mole, and yet it's a liquid instead of a gas at room temperature. Here's the chart I was kind of wanting to see the other day. If we graph the boiling point of substances versus the period of X, what does that mean? These are all group 6 elements: tellurium, selenium, sulfur, and oxygen. They're all in group 6A. And so they all form compounds with hydrogen of the form H2X. So tellurium is in period 5, selenium in period 4, sulfur in period 3. Do you see a trend in the boiling point? Yeah, it looks like it's not a perfect line, but it's linear, right? That looks like, draw a line, something like that. So just looking at these three, we would expect the boiling point of water to be around minus 100 degrees. What types of intermolecular forces do these three compounds have? Well, everything has dispersion forces. Are these molecules polar? Well, you can't, oops, I didn't mean to do that. You can't always just figure that out by looking at them. Here, I'll draw the Lewis structure for dihydrogen sulfide. Is that polar? Yeah, because it's got lone pairs in the central atom. These all have the same Lewis structure. All you do is change the S to something else. They're all polar, so then they have dipole forces. The dispersion forces get stronger as the molecule gets larger. Tellurium is a larger atom than selenium. Selenium is larger than sulfur. And so this trend of boiling point increasing as the molecule gets larger is reasonable. Oxygen is smaller than sulfur, and so we would expect that it would follow this trend and be down here. Water has dispersion forces and dipole-dipole forces, but what else does it have? Hydrogen bonding. Hydrogen bonding is the strongest intermolecular force, and because it has that additional force holding the particles together, its boiling point is much higher than we would predict. And it's a good thing, because life wouldn't work out so well if water boiled at minus 100 degrees Celsius. All the lakes, the ocean, all the water in your body would all be in the gas state right now. That just wouldn't work very well. So life depends on water having this high boiling point. Water is also very polar, and that allows it to interact with a lot of other polar and ionic compounds. Water is often called the universal solvent because it will dissolve a lot of things. And water is one of very few compounds that are liquids at room temperature. What other compounds are liquids at room temperature? How about rubbing alcohol? Rubbing alcohol is a liquid at room temperature. Gasoline. But a lot of the things that we deal with as liquids, like, oh, well, shampoo's a liquid. Yeah, but it's stuff dissolved in what? Water. Blood's a liquid, but it's got water in it. Water is a liquid, it's got other stuff in it. Most of the things that we encounter are actually solutions of stuff dissolved in water. And the reason that water can dissolve so many things is because of its high polarity. Mercury is a liquid, yes. Mercury is a liquid at room temperature. But there's not a lot of liquid mercury around, is there? No, and it's dangerous. It's really, really cool. It's fun. But unfortunately, it's toxic, and so we can't just, be playing with it all the time. I think we all recognize that life is impossible without water, and I think that's especially relevant right now. California's in a drought, and here we are in the Central Valley. really concerned about our water supply, right? Because without water, life can't exist. Certainly not life as we know it. The way water freezes is unique. Most things, when they go from a liquid to a solid, they become more dense because the particles arrange in a fixed pattern and they're a little closer together. Water is unusual in that its solid is less dense than its liquid, and this causes ice to float on water. And this is really important in the environment because if ice was more dense, see, I grew up in Minnesota. Minnesota, it says it's the land of 10,000 lakes. It's a lot more than that. But it's also a very cold place in the winter. If ice froze, what would happen in the winter is as the ice on the top of the lake froze, it would sink. And the lake would freeze solid. And all the fish and turtles and everything in there would die every year. So that wouldn't work out very well. Also, the polar ice caps, big hunks of ice, some of them are over land, but some of them are over water. If ice was more dense, that would sink as well. The frozen layer of ice coming to the surface of the water actually helps to insulate the rest of the lake so the lakes don't freeze solid. They do freeze thick enough that in the old days they used to lay train tracks across the ice and run freight trains because there's so many lakes that you can't really have a straight shot railroad, and they do all this logging and then they need to get the wood out, and so they'd wait for the winter when they could lay train tracks in a straight line and bring it out quickly instead of building railroad tracks that swirled around all the lakes. Water, because it's less dense when it freezes, it expands. And you may have observed this if you ever put a soda or a full bottle of Gatorade or some water in the freezer, right? What happens if you put a can of soda in the freezer and forget it? It explodes, right? It'll just absolutely explode. Why is that? Because the water expands, right? This is the reason that pipes freeze. We don't have to worry about that too much around here because it doesn't get that cold for that long that pipes freeze, but in Minnesota and other northern climates, it's a serious problem. You go away in the winter, and if the power goes out and your heater fails, you come home and the water pipes have burst inside your house, and there's like floods of water running around. It's really not pleasant. This is also the reason that plants die in the freeze. The reason that freezing temperatures damage oranges. Because in the cells of living organisms is generally a lot of water. And when those cells freeze, the water expands and it breaks the cell walls. And so the oranges turn to mush. If you buy frozen vegetables, at the store, they tend to turn out better than if you try freezing them at home. And the reason is that they do flash freezing of vegetables. They freeze them so quickly that the water does not have a chance to line up in its crystalline form and expand. And so that preserves the vegetables a little better. But there are some things that you just flat out cannot freeze, right? You can't freeze lettuce and expect it to be good later, right? That's not going to work out. It just turns into mush. So any questions about water? This is the chapter in review.